Section 4.1.2, End Behavior. A graph's end behavior is determined from the equations leading power function. This is the term with the highest exponent in a polynomial function. So before we talk about the possibilities for end behavior, let's drop down to example 1. We have a polynomial function given in example A, happens to be a 4th degree polynomial function, and our leading power function is simply the term with the highest exponent. So in example A, our leading power function is x to the 4th. If I can identify that leading power function, which you can see is a pretty easy thing to do, then I can predict the end behavior. So when we learn the connection between the leading power function and the end behavior, there's 4 possibilities that can occur for the end behavior. So I've got 4 grids drawn here, and we're going to look at some examples of polynomial functions. Now remember, a polynomial function is smooth and continuous. It does its twisting and turning in the interior. It can do that any number of times. And then eventually it establishes its end behavior. So the dotted line there in the middle is just to show the polynomial's going through all of its activity there in its interior, but we're looking at what's going on the extreme left and right sides of the graph. In this case, if we look at the left side, going from the origin to the left, we can see that the graph rises. And then if we look to the right, center yourself on the origin in the middle and look to the right, clearly the graph falls. So in this case, we have opposite end behavior. Another possibility, again, let's draw a polynomial that's smooth and continuous. It can do whatever it wants here in the middle, and let's suppose it does something like this. In this case, the left side falls and the right side rises. So those are 2 opposite possibilities for end behavior. Another example would be a polynomial that does something like this. Again, it can do all of its activity in the middle. And in this case, the left side rises and the right side rises. Or we can have just the opposite of that, maybe something like this, where the left side falls and the right side falls. These 4 cases can be coordinated to establish some patterns. Notice in the first 2 cases, we have opposite end behavior. This will occur when our leading power function is of odd degree. Notice the O in opposite goes with the O in odd. So if our leading power function has an odd exponent, then we're going to obtain opposite end behavior. And in that case, we can compare it to our most basic odd degree power function. If I think about the cubic function, y equals x cubed, which, remember, squiggles its way through the middle, the left side is going to fall and the right side is going to rise. So if I can identify the leading power function and I notice that it's of odd degree, if the leading coefficient is positive, it's going to do the same thing that the function x cubed does. Now, if it happens to be multiplied by a negative, remember negative x cubed would be reflected across the x-axis, then I'm going to match the same behavior there, and we'll do some examples to clarify that. Now, the other big category that we have here is these 2 cases. In this case, we have the same end behavior. Both sides rise or fall. This occurs with an even power function. Either both sides rise or both sides fall. We can compare any even degree leading power function with our x squared, our most basic even degree power function. That is y equals x squared. For a positive leading coefficient, we know that x squared opens up. Both sides are going to rise. Or if we have a negative leading coefficient, we know that reflects the graph across the x-axis, and in that case, both sides would fall. So we're going to identify the leading power function and associate it either with the basic odd degree power function or the basic even degree power function. Let's go back to example 1. We've already identified the leading power function as x to the 4th. So I'm going to make the observation that this is an even power function. So I'm going to compare it to the most basic even power function. We've studied that extensively. That was one of our parent functions. And we know that x squared does something like this. Therefore, we can say for our given function f of x, the left side and the right side both rise. And we could verify that on our calculator. So I'm going to go to y equals, and I'm going to type in the given function. And take a quick peek at the graph to observe the end behavior. When that little wheel is turning in the top right corner, it simply means that it is still graphing. Okay, I didn't get a result, so let's go to our zoom button and let's go down to the bottom of the list here. This is always a good thing to do if you can't see your graph. I'm going to choose option number 10, zoom fit. Okay, that's going to readjust the window. It's going to go out and figure out where did that graph land. It just looks like it's increasing very quickly. And then it will show me an appropriate screen. So we can see that the left side rises, the right side rises, so our prediction is correct. Okay, now how do you get back to that standard viewing window? Just go zoom. Option number 6 is standard and will be set up for the next example. Okay, example B, g of x equals negative 3x cubed plus 2x plus 1. So we'll start with our leading power function. The leading power function is, in this case, the highest powered term together with its coefficient, negative 3x cubed. This is of odd degree, so we can expect opposite end behavior. We just have to figure out which is which. So negative 3x cubed is going to compare to our negative x cubed function up here. Okay, the left side is going to rise and the right side is going to fall. And again, we could certainly verify that very easily with our calculator. On example C, it's not as clear what that leading power function is because this is in factored form. So what we want to do is anticipate if I were to multiply that out, what would our highest powered term look like? Now, that would be a lot of work to multiply all of that out. So I'm not going to do that. I'm just going to anticipate if I did, what would our highest powered term look like? So for example, if we multiply those two together, our highest powered term would be an x squared. Right? If I FOIL this out, my highest powered term would be x squared, and then I've got an x to the power of 1 down here. If I multiply all of those powers together, remember we add exponents when we multiply the powers, we would end up with x to the 5th power. So we can determine that our leading power function for m of x is x to the 5th power. Notice here I can just sum all of the exponents on the factors and obtain the same leading power function. This is an odd function, so I would expect opposite end behavior. Since it's odd, I'm going to compare it to our most basic odd power function, which is x cubed. X to the 5th is going to do the same thing that x cubed does. So the left side falls and the right side rises. One more example here, one little twist to consider. We are looking for the leading power function. The leading power function is the highest powered term, not necessarily the first term. This one's out of order. This is in ascending order, not descending order. It doesn't go from the highest exponent to the lowest. It goes the opposite way. But my leading power function here is negative 5x squared. That is an even power function, so I should expect the same end behavior. So I'm going to compare it to our most basic power function, x squared. X squared does something like this. However, because we have a negative leading coefficient, we know a negative would reflect a graph across the x-axis. So in this case, both ends are going to fall. So the left end is going to fall and the right end is going to fall. Notice that is a familiar parabola, and we said the sign of the leading coefficient indicates the direction of opening. So we already know this is a parabola that opens down, and that's the result that we have obtained here. So the big idea on this section, to determine what happens on the far left and right sides of a graph, we identify the leading power function, and we make the observation, is it even or is it odd? If it is odd, it's going to follow the same behavior as either positive x cubed or negative x cubed, depending on the sign of the leading coefficient. If it is even, then the graph is going to follow the same behavior of either positive x squared or negative x squared, again, depending on the sign of the leading coefficient. Now, if that gets confusing, don't forget your backup plan. You can type every single one of these graphs into your calculator and observe the end behavior to verify what you predicted. Don't forget about your Zoom Fit option or Zoom 6 Standard if some of these graphs grow very quickly. Okay, hope that is helpful. See you in the next video.